these dots side be like connected ones that you want to count as long as they're contained within this, or you can just kind of ignore that?
Yeah, so the lung is supposed to have full holes in it because those are your bifurcations of the bronchi that go into the lung.
Oh,
You mean the dark spots, right?
yeah, like the black parts in between.
Yeah, you're supposed to have stuff.
Oh, okay.
This is made the
binary opening.
I'm muting you.
I thought I was muted.
That's okay. Okay, it's good now.
Okay, so the binary opening closing is not the only way to do it.
Mm-hmm.
But basically, we're just asking you to smooth the image. And so there are, like, for example,
Is the binary opening closing getting rid of the stuff on the outside of the lungs that are like that shouldn't be there, or are they getting rid of something else? I was a little confused with what like the binary opening and closing is supposed to be doing.
so
Or what binary closing method is it?
so it's supposed to kind of get rid of the two of them together are supposed to get rid of like tiny little specks, either like little things that jet out,
Mhm.
or things that or like little holes that like should be. But obviously,
So you do both binary closing and binary opening?
when you do them together, it does a smoothing effect.
Oh,
That's
okay.
not the only way to.
I only did the closing once. Maybe I should do both.
Yeah, if you do opening first, anyway, is this correct? If you do opening first and then you close, then you get a smoothing effect, right?
Like a hole filling effect? Oh yeah, smoothing effect. Yeah, that's what you talked about in class today if you were there.
Yeah.
But there's a function that does both for you too.
All right. I'll check that out.
That's perfectly legit to use as well.
I have a question. In this cell over here, what exactly are you getting at with this? True.
Yeah, so that might have been confusing. But I include a lot of my own sort of like intermediate steps.
Oh.
Like that's my way of just trying to show to hint at the fact that it might be useful for you to threshold something. For example, if you actually looked at the pixel values after you did like the threshold, like let's say you did like ball less than threshold, right? Like if you actually looked at the pixels are now like booleans, like true and false. But I was trying to hint at that, like that's how you should try to do it. I feel like a lot of the hints end up confusing people more than it ends up like helping people. I thought it was in people's favor, but
You said opening first and then close.
yeah, okay. Because you went over like structuring elements and stuff like that, right?
Yeah.
In class. Okay. So if you just imagine like take some object and like do a binary opening on it and then like do binary closing, so I think we probably have to check me on this explanation, but like let's like if some things are like almost touching each other, the opening will like then go ahead and connect them, right? And then like let's say that you have like closing, things that are too thin, we'll go ahead and like remove them.
Okay.
Yeah,
that's right.
Sounds right. Okay. So that's what we're asking.
It's one or the other.
Yeah.
Yeah. So, okay. Any other questions that I haven't answered yet for the homework?
I have a question.
Go ahead. Yeah.
I think I'm getting some feedback. I hear my voice kind of echoing. Okay, now I think it's better. So yeah, my question is about part 6. Well, I wrote something that in order to loop through the whole volume and check each pixel whether or not it's labeled as a small volume, that's order n cubed, and it takes a really long time to run. So I'm getting the sense that this is not the correct way to do it. Is it supposed to take a really long time, or is there a faster method we're supposed to be using?
So are you trying to implement algorithm 2 in step 6?
Yes. And so
okay.
Right. So I mean, it's easy to, I know how to label the volumes just using the package, and that actually happened pretty quickly just using the property measurement. But then so I can get those tags that go with the small volumes, and when I try to just delete them or make them homogeneous with the large volumes so that they're not visible, I've been looping through the whole image volume, and it takes forever because it's order n cubed. And so usually when something takes that long to run, I think I've done something wrong or maybe not used the right method.
So there's another method that goes along with the label method that's very useful.
Okay.
Called region props.
Called what?
Region props. I'll post the link in the chat. Wait, is that what you've been using?
Well, that's what I used to apply the labels, and then it made about like 100 some volumes, and they each had their own label. But then once I have those labels, I don't know how to manipulate those little volumes, because what I really wanted to do was loop through those hundreds some volumes and manipulate them by changing their labels or whatever. But I don't know how to do that using those using the props. Is there a way to directly manipulate those volumes?
Let me think. So one of the region props, like one of those 100 something volumes, will correspond to essentially like a rough segmentation of the lungs.
Yeah.
So you can really just take maybe that one and start from there.
Okay, so like
you can discard like most of the other ones.
Okay. All right, that makes sense. I don't have my computer in front of me, but it's so like I could I could call my whole new volume, just set it to that. Because it's just, I have labels, but then I don't know how to actually access those volumes to manipulate the labels or just change them so they equal the label of the large volume, which was my approach. But then I don't know how to do that, because it seems like the region props just gives you information, but it doesn't allow you to directly manipulate the image that you're working with, unless I've missed something.
Well, the region props will contain enough information for you to reconstruct a new segmentation. Like, for example, it'll include all the coordinates of the pixels within the...
Oh, okay. Okay, so I'll just look some more at what those, because it gives you a whole lot of different pieces of information.
Right,
So,
right.
All right, I'll try that.
Sorry. Do you have these region props?
I would say the most straightforward is to use region props. What do you think?
So
I definitely use region props.
you use for step 6 you did?
Yeah. Because for me, labels and region props, those two functions like almost always go together. And that made things like very easy for me.
So the labels just give you like some value that corresponds to like some component that a single pixel's in, right?
You know, like the connected components
Yeah.
thing? Yeah, so what label does is that it just goes through the entire like 2D or 3D image, and it just it finds all the connected components, and each like series of connected components, it labels like the same thing, like 0, like 1 or 2. And then what you do is you pass that label matrix into region props, and that gives you a really nice like list of objects, like region prop objects that like are computed geometric features of all the different sets of labels.
Yeah, that's exactly what I did. It was just the last step of how to get rid of those little objects that it's identified that I didn't know how to do. But maybe I just need to look further in the region props in what it gives you.
Yeah, definitely.
Okay.
So when you're talking about volume, you actually have to not just do it on a per slice for the pixel, you have to do it on the whole volume. Because what I did is I just looked at, for each like connecting component, I just looked at the total size, and said if it's below some threshold, you set it to like the 0 value, which is like deleting the component. Is that not what you're supposed to do? Or
no, that's totally fine.
Okay.
Totally fine. And then as for per slice or for the entire image volume, that's really up to you to decide. Okay. When I did it, I found that one works better than the other, but it wasn't like a huge improvement. Because when we had the assignment last year, it was more like open-ended, so you could really do whatever you want. So one of the questions I felt to investigate was like, is per slice better than like using the entire thing?
So region props is kind of like a per volume way of doing it, or the volume way of doing it.
So the per slice way of doing it is for each slice, you compute the optimal threshold, using like Olthu's method, and then you call label on like just the splice, and you call region props on just the splice. And then you do it that way. But if you want to do the volume method, you pass in the whole 3D image volume to Olthu's method.
So that's actually the way I did it.
Yeah, that one's definitely the easier way because you don't really have to reconstruct anything.
Yeah, the label function, you can just pass the entire volume into it, and what you get out is like the whole volume with like
3D label, like something that's 3D labeled essentially, right?
Yeah, like the 3D
all the connected components. Like if there's some like ball inside your volume, it'll have its own like integer associated with it inside your volume, and then the trick comes like to figuring out which one of those numbers is your lung. Yeah. But once you figure that out, you can just set everything else to false, but your lung to true, and then you get a Boolean volume where just the lung is true.
So
yeah, sorry, go ahead.
Oh, what I did, I just looped over like each slice, and then for each slice I call the label function, and then for each like labeled output for each slice, I said, okay, which are the ones that are touching the edges, remove those components, and then which are the ones that are like have less than X number of pixels, and remove those also.
Right.
Is that an okay way to?
Yeah, it's only fine.
Yeah,
like the post slice version.
Okay.
Yeah. Which.
But I didn't use region props or.
Oh yeah.
Okay.
That's cool too.
Okay.
Yeah, you don't
have to.
Okay.
Yeah, if you get the result and it's robust to different patients, then you're good.
Okay.
Yeah. Does that answer your question? Is this who's on?
Debbie.
Okay. Does that answer your question, Debbie, or?
It does. No. Thank you. Yes. I must say I'm a little curious to know what the method of that region props, how it does it so fast, because it extracts all this information about the whole volume. And it does it way, way faster than you could loop through all the pixels individually. So do you guys know, and this is mostly just curiosity, but do you know what kind of algorithm it uses?
I can check it for you right now. It's open source. I found the code. I don't want to read through it.
It's probably a lot.
I posted it.
Oh, thank you. Yeah.
Yeah, like, but because I really don't know.
Some of it is like pretty intuitive. Like if you look at some of the methods, like one is just area, and that kind of just like returns a sum of like all the pixels within it. Does that make sense? But like some of them are less obvious.
Yeah, it just does it really fast. It gets all that information about the whole volume so fast.
Right.
Yeah, that answers my question. Thank you.
Yeah, well, probably not looping through.
No.
No.
I don't think.
Probably,
Okay. Any other questions?
I just have one final question on the bonus part. I don't know if you're allowed to give advice on that.
You can ask your question and
I was just wondering, I was looking at the trachea one, and I was wondering if what kind of expected to accomplish that part is like, I remember you talked about in the lectures, like finding things that look like tubes was part of like something that we went over. Is that like the algorithm that we would generally use to like find the trachea and like segment it out?
So the bonus are totally open-ended. I'm sure that everyone will come up with their own way to do it. If you can do it and you can show it and prove that you've done it, that's all we care about.
Okay.
Yeah, you can use whatever tools in your toolbox.
Cool.
Yeah. If tube finding is your way of doing it.
Okay.
I'm just wondering what will be a solution. Yeah. Okay. Anything else? Any other questions from any of the Zoom participants? Are you guys here for the deep learning tutorial then? Or any responses?
no.
Okay.
No question.
No question. Okay.
Thank you guys very much.
Okay. See you, Alex. Okay. But how many people are on Zoom right now?
Just Debbie and Shrikar.
Shrikar? Okay. Debbie and Shrikar, are you here for the deep learning portion, or do you have some more questions for homework 1? No reply?
Debbie says both. And she's done with questions.
No questions.
So
okay. I just want to know
deep learning.
if I should start on the deep learning portion. All right, I'll start on deep learning questions. Cool. Okay.
Oh, I did have one question.
Yeah.
And like, when you do like the OS lister,
Yeah.
like the first index, you know, I've always been getting like this .ds store thing.
People with Macs will have that. Yeah.
Okay.
You can filter it out.
That's what I did.
You can use an end with statement in Python.
Mhm.
Like, if not, like you can do if not, like the path ends with ds.store or whatever.
Wait, what about like the wildcard stuff? Like, do you do list or like with the asterisk .dcm? Does that work?
Oh, I think that works too.
Like,
yeah.
it'll only list files that end in .dcm.
I mean, I just filtered it out, but I wasn't sure if it was like useful for anything.
Oh, I think it's a Mac thing.
The Mac thing.
It's a Mac thing. Mac adds that for some reason. I don't.
It's so annoying when someone zips the file on their Mac and sends it to me, and then I have .data stored too.
On your window. Yeah. Yeah, that is annoying. It happens to me a lot too. Yeah. Should probably write the code to account for that. Okay. Let's see. Let me make sure I close everything else.
Are you doing a PyTorch intro v2?
Yeah. So
Okay.
this is so if you open up PyTorch intro v2, and you want to follow along, that's the one I'm using right now. Do you have this opened up?
Yeah.
Okay. And Debbie, do you, the Zoom people, do you have this opened up? Do you need time to open it up?
I'm at work, so I don't have that
Oh.
opened up, but I'm just going to watch and take notes.
Sure. Okay. All right. So the reason why we use PyTorch is for the following reason. So let's say that you have a couple of variables, right? Let's say, so I've used this as a dummy variable where there are these operations that are done on variables A, B, C, D, and E. So for example, I made this dummy variable A in PyTorch using these commands here. So PyTorch allows you to, you don't have to do it this way, but since we all know NumPy very well from homework 1, I made a NumPy array, and as you can see that this is just a vector with 2 elements in it. And you can do this operation torch from NumPy, and you can convert R here into what's called a PyTorch variable. And the significance of this variable is that the variable will allow you to connect the variables by the operations done on each one. So like an operation would be done to A, so A squared, so this is A to the power of 2, is equal to B. So this is the operation that connects A with B. And so every single one of these is a PyTorch variable. And what they call this is a computational graph. And TensorFlow uses the same concept as well. It's like they're constructing like the relationships between all the different variables. And so you can see what I did with C is I made C is equal to A plus 1, and D is basically the sum of C minus B, and then E is like C divided by 2. And essentially what you can see here is that if you trace D, if you look at these relationships here and you trace A and connect it back to, take D and connect D back to A through B and C, what you'll realize that you are summing all the elements of A plus 1 minus A squared, because A plus 1 is C, and then A squared, that was B. And notice here that like we're doing this sum operation, so you're summing all the elements together. And so this is a sum over the elements, just to be clear, is what that means. And all the variables will automatically come with this field called grad. So I'm going to go ahead and execute this here. Run. And so as you can see, the NumPy, it's at 0, 1. the torch variable is the same thing, 0, 1. It tells you the sort of type of torch variable it is. So this is a double tensor of size 2 because there's 2 elements. Here I printed out gradient, but right now there's no gradient, and you'll figure out why soon. And I also printed out 2. That should make sense because A was 0 and 1. 0 plus 1 was 1 minus 0, so that's 1. And then the other element was like 1 plus 1, that's 2 minus 1 squared, so that's 1. You add those together, you get 2. So that makes sense. You can sort of follow that through in your head. So this is obviously a trivial example, but it's meant to be trivial so that you can follow along. So what happens is, if you do the algebra for this, or the calculus for this, you do the derivative of d, which is a scalar, right, because this is a sum of elements. The d is kind of supposed to be like your loss function. The gradient of d versus respect to a, you take the derivative of this, what do you get? So the derivative of this term here is just 1 because you have a here. The derivative of this term here is 2a, all right? And then you'll have to sum them together, right? And so if you take d and you call the method backwards, if you call d dot backwards, then after you do that, a dot grad now has, instead of being none right here, it actually has the gradient of d with respect to a inside of it. So I run this, and you get 1 minus 1. That makes sense, right? Because the derivative of this respect to a, when a is 0, you would get just 1 for the first element. So that's just 1. And if a is equal to 1, you get 1 minus 2, and that's minus 1. So that makes sense. You can sort of do that in your head. And that makes sense. This is the gradient. And so we did it for a trivial example, but essentially the same thing applies when you have millions and millions of like a's, like millions and millions of essentially parameters, like in a neural network, which is why we use TensorFlow and PyTorch, is because of this automatic gradient calculator that they give you, so you don't have to do it all by hand. All right, okay. And so yeah, this is just like the standard function, the standard update rule, right? You have to choose some learning rate. Once you have that learning rate, you can take this gradient that we've calculated for every single variable and apply it to update your weights, right? So this is an example here. So we have we're passing a as the thing that we want to update. We have a learning rate of 1 so that we can follow along. And then so we do this step right here so all of these will hold a gradient in them, and you don't want them to accumulate. If you don't want them to accumulate, you have to zero it out before you call the backwards function, so that it's just the most recent gradient and not like an accumulation of all the previous gradients, like the previous times you called the backwards, right?
Wait, what do you mean by accumulate? It's like,
let's say that I just keep on. Yeah, it'll just add together the previous. Let's say that I execute it twice. They'll take the previous gradient and then add on top of it the current gradient.
Oh, sort of like double.
They'll just like
Sums it up.
Yeah, they'll sum it up.
Like a plus
if you don't.
equals. Like a plus equals.
Okay.
Yeah, it'll be like the plus equals.
Okay.
Yeah. Which you may want or you may not want.
Right.
But just so you understand that that's it's like sort of default function. I'm showing you that there's a zero grad thing that you should call if you don't want it to behave that way. So then I call d backwards, and then I show you the gradient, which is as you would expect from the previous one, 1 minus 1. And then, as you would expect, if you add that to the current a, you should be getting, with a learning rate of 1, so like, you should be getting gradient minus, so 1 minus 1 minus 1 would be 2. And then 0 minus 1 times 1 would be minus 1, right? So does everyone see how this was the initial A, this was the gradient on A, this is what A looks like after you apply the gradient to it with a learning rate of 1, because you're doing that minus the learning rate times grad. Okay, too basic perhaps. Okay.
Wait, is everyone here familiar with like neural networks and stuff?
Yeah.
Oh, okay.
Getting
Is it clear to you why we need to compute gradients?
Not really.
Okay.
Yeah.
Okay.
Shall we
Hopefully it'll
explain
become
that?
more clear as I go along.
Okay.
And it'll be more clear once I get to the part about loss functions. And if you, at that point, I'll stop and sort of answer some more questions.
Okay.
Yeah, we'll get to loss functions. So just this is, I wanted to do it this way, just like, because based on calculus, we kind of all understand what gradients mean, but then it'll be, hopefully this will be more clear why gradients are important for deep learning later on though. So I'll present like the task first, okay? So this is like the very standard intro to deep learning data set, which is like the CFAR 10. Kind of what everyone uses like as their sort of intro to deep learning. Basically, in this CFAR 10 data set, there's like these 10 classes, and the task here is to try to take an image that is 3 by 32 by 32, and then classify it as one of these 10 things. So it's airplane, automobile, bird, cat, deer, dog, frog, horse, chip, truck. It's 3 because these are RGB images, red, green, blue, and the height and width are both 32. So there's, they're square images. And okay, let me just make sure we have the dependencies here. So this is just this is like, because this is, you don't when you have your own data sets that you want to do deep learning on, you'll have to like scrub them yourself. But PyTorch comes with the preloaded data sets already for you. So you can load it into this thing here. They call test loader and train loader. Basically, every time we call this, it like grabs a batch for you, which is very convenient. And by the way, if you don't know what a batch is, all it is saying that, like, let's say that I have a batch size of 4. A batch is just saying that I want you to sample from my data set 4 images and their labels. So it's just give me 4 of these 3 by 32 by 32 images along with another vector that just tells me what each of those 4 things are. So like, give me something that's like a vector that, let's say cat is like 0 and deer is 4 and plane is 3. So like this vector would be 0, 4, 0, 3. This allows you to train your neural network piece by piece from your data set.
And this data set is intended to be rotation invariant. Is that cat sideways?
Yeah, I think this is a cat sideways. Yeah. Yeah. So that's the other thing about these networks is that usually when you train these things, I don't know if this data just might have this cat sideways, but it doesn't matter because most of the time what people do is they'll actually as they show the neural network these pictures, the neural networks will be shifted a bit. Like you'll deform it somehow to try to get the neural network to recognize it, no matter what form it comes in, whether it's upside down, side by side. Some people do like kind of a little like a translation up and like down by a little bit. So like so that this deer is like a little bit closer to the right side in one exposure to the image, a little bit this way. And people actually play with the contrast and like it may also sometimes help to like apply to sharpen the image or blur the image, things like that. Those things are all things that people do.
Make it more robust.
To make it more robust to see, images. Okay, so I'm just going to display them like, so just grabs around. Every time I hit the cell, it'll grab a different set, as you can see, right? Yeah. And so this is just my way of showing you what it looks like. So it has already, PyTorch here, at least for this instance, has already normalized images for you so that all the pixels are between -1 and 1. So that's why I've proven that to you with this. And I'm also proving you that what the images look like. So it's 4, 3, 32, 32, because this is a batch size of 4. And then each image is 3 channels with 32 pixels in the height and the width. That's why that is the way it is. Okay. And so in this particular lecture, in class, we're going to have you go through Ming-Ray's machine learning tutorial before doing this. But in this particular, we're going to jump right into convolutional neural networks. So hopefully this won't be too hard of a jump.
And you guys have seen convolution before in class?
Yeah.
Okay.
Okay.
Cool. Yeah.
So, but you've learned convolutions more like in the electrical engineering sense, right? Like
Flip
with
Or
kernels,
filtering. Yeah.
like for
flip and
filtering.
shift.
Right. And so like in this, so it is similar. You know, you've learned about convolution so that you can do an operation to an image that will either sharpen its edges or like extract edges or like blur it on purpose, for example. So the same thing is happening here, except this is an arbitrary filter that's going across the image. So this is a toy image that's been padded with zeros, and then it's an image that has integers in it. But let's pretend, for example, that the filter you're using is this 201 filter, 100, and then 011. So in this corner here, because the only one that is, so there's a 0 over this one, and also a 0 over this 2, and also 0 here. So actually, if you watch this kernel or this filter move over this image, the only one that actually generates a positive output is this lower right-hand corner here, which is why this upper left-hand corner here is a 1. So that makes sense to you guys? Sure. So watch this kernel. So see this how this kernel is 201, 100, 011. When this overlaps with this corner up here, the only positive number occurs. So you're multiplying the elements of this kernel by this 3 by 3 square here, right? So notice how only the lower right-hand corner of this kernel, which is 1, generates a positive number when you multiply here, because everything else generates 0, right?
Is there a reason why it's jumping step by like skipping a row?
Yeah, so that's supposed to mimic the fact that the stride here is 2. Okay. So like in your convolutions that you probably learned about, you probably were doing it with the stride of 1. So like we jump from here to here to here to here. This one's jumping from this square all the way to this square here. So your stride here is 2. Okay. Are you following? Does that make sense?
No, I don't think I.
Okay. So this is just the normal convolution, maybe like you saw in class. So you see that 3 by 3 matrix that's like going around your, I guess, 5 by 5 image. So the smaller box, whatever it overlaps with on the bigger box, it does like an element-wise multiplication. So like the smaller box, there's numbers on the like lower right-hand side corner. So like it'll just do a multiplication with the bigger number in like the blue box. And then once you do like all those 9 element-wise multiplications, you just sum up all the products, and that number goes into the green box on the right. Does that make sense?
That makes sense.
Yeah. Yeah. And so likewise, like in the center, notice like just to verify. So this is a 3 by 3 square. In the middle, like when you do element-wise multiplication with these 9 pixels in the middle, with the kernel that you're seeing here, you get an output of 10. Okay. Which is why the 10 is the one in the center. So in some sense, for example, if this was a kernel that was like all 1s, for example, you would get that smoothing effect, right? Like
so if it was all 1s, you'd basically just sum up all 9.
Yeah, it's like a moving average.
If this kernel was instead all 1s, then this upper left-hand corner here would be like 2 plus 2 plus 1. Okay. Right? Hello.
So different, like the values that you set just give you like different properties, I guess.
Yeah. So basically, this will become hopefully clear later on. Is that these in a neural network, these are randomly initialized, and then you allow the neural network to learn whatever filter is useful for itself to interpret the images. Yeah. Hey Phyllis, are you here for homework 1 help or for tutorial?
Yeah, just want to do the setup.
Do the setup?
Yeah, I wasn't here, like.
Oh, it's okay. You mean for homework 1 setup? Okay.
If I really around to the novel, like, so I haven't tried it out. I don't know.
Okay. You
I can help.
You could help that, and I'll just continue with the program. Yes. Okay. Or we can do it afterwards if you want. It's up to you. Okay. So don't worry about if you don't understand how this fits. Like if you don't understand how this fits in the bigger picture, that's okay. as long as you understand like what's happening in a convolutional operation. Like, well, I'm doing a convolutional operation to transform this image here into this image here. Okay. And as long as you understand that, you're good for at least this portion. Okay. So, for example, here is we're using a 3 by 3 kernel. So this kernel here, this gray box that you see moving around, is 3 by 3, and we're applying this to a 5 by 5 input that's been padded with a 1 and a padding of 1. So this is 1, 2, 3, 4, 5. So the input is a 5 by 5 image that's been padded with 1 layer of zeros. And so and here, yeah, this is just a summary of what the kernel weights are here in case it's too hard to follow it. It was 2, 0, 1, 1, 0, 0, 0, 1, 1. But the way that you figure out what the size of the image is after you apply the kernel is there's this very convenient formula here. So like the new width, and this obviously applies to the height. So the new height or the new width is equal to the old width minus the filter size plus 2 times the padding that you do. So here, padding is 1 because there's only 1 layer around the image. The filter size is 3 because our kernel is 3 by 3. Our sprite is 2 because as you notice, this thing jumps by 2 pixels, not by 1 pixel every operation, right? So that's why it jumps to the middle, then it jumps to the edge. It would be doing operations 1, 2, 3, 4, 5 times if it were striding by 1, but because it's striding by 2, it's only doing 1, 2, 3 operations per row, right? And so as you can see, if you plug those numbers that I just described into this formula here, you get 3. 5 minus 3 plus 2 times 1 divided by 2 plus 1. And so you can see like that the output of applying this convolution to this image is 3. That makes sense? Following along? Yeah. Okay. And so one thing that you'll see a lot of times that these things are summarized by these sort of like flow diagrams like this. And the reason why they're doing this is they're kind of implicitly saying something. Like they're saying, so this is the image, right? And convolutional operation is done to it that then turns it into this. And you sort of you can think of it as like this right here is like some 1-channel image, right? And that would be this. And then this right here is some 1-channel output, which is this. But in reality, let's say that we did like many different kernels. Like let's say that this image, instead of being 2-dimensional like we have here, it was like 3-dimensional, as in there was 1 of these for each of the color channels. Then this would be a volume, right? This image would be a volume where there's 1 of these 2-dimensional matrices for each red, green, and blue. And then you apply this kernel, and this kernel, instead of being 3 by 3, let's say it was 3 by 3 by 3, right? Then you would apply this kernel through all of the channels at once, producing each one of these numbers here. And next, you could have several of these 3 by 3 by 3 kernels, in which if you had several of these 3 by 3 kernels applied to a 3 by 32 by 32 image, let's say that you had, let's say that you had 8 such filters, right? Then you would have 8 of these filter maps, right? And that's why they oftentimes will show that the next representation of the image is usually thicker in the channel dimension than the original image. Because this would be as if you had an image that was height by width by channel, and then now this, let's say there's 64 filters, it would be 64, let's say that this was still like a 3 by 3, it would be like 64 by 3 by 3, if you had 64 such of these 3 by 3 kernels applied to it. Still following? Okay. And so lastly, after so each one of these is, they'll call it being the activations or the image is being compressed. Because usually what you do is when you take an image and you go to the next step, you have a lot more filters. So like you'll go from having 3 channels to then having 64 in this direction. But then like in the height and width dimensions, it'll be smaller, right? And so it's kind of like being compressed, quote unquote. Eventually, you take your compressed portion of the representation of the image, and then you'll flatten it out, And all that means is that you take each one of these activations here and you just lay it out in like a straight line. And then you'll do to that what's called an affine transformation, which is just this. So this is an example of affine transformation. Let's say that you take all these activations here in this box and you lay it out into a straight line. And so you've kind of lost kind of like the spatial relationships as you do that, right? So like before, you know, like this activation right here, you could safely assume sort of represents the upper left-hand corner of this image. And like this activation, any of the activations that are going through the center of this cube this way, you can safely say are a result of transformations from things coming from the center of the image. But once you lay it out flat, that is no longer true, which is fine. And so like, let's say that you laid it out this way, the affine transformation is taking a set of weights here, multiplying it by that flattened out representation of the image, adding a bias term to it, and then getting the output. This is just a way, this is taken from the CS231 and lectures. Basically, when you do this, it is the same as just taking your bias and like concatenating a bias to your weights and then multiplying it by your activations with a 1 at the end of it. Because if you just look at this, these two operations are equivalent to each other, basically, is what this is saying. And this is an image from, I think, from Coursera, basically, that I took that just shows, you know, the affine portion of the convolutional neural network, which usually happens at the very end, is pretty much just the same thing as like your vanilla feed-forward neural network, which I think most people, are you guys familiar with what that is? Okay. But basically, so if you're not familiar with this, this is like the most standard type of neural network, which is basically saying like, if you have these inputs x1, x2, x3.
Oh wait,
like,
listen.
Yeah.
Debbie is not familiar with whatever you just said.
Feed-forward neural networks.
Yeah.
Okay.
I don't know what you said.
Yeah, no problem.
Okay.
Okay, so I'll do a quick thing of feed-forward neural networks. So this is like this is usually whenever you learn about deep learning, they'll probably show you this image like as like the first thing they'll teach you. So this is a neural network. Basically, this is a neural network that would be very bad at interpreting images for several reasons, right? But this would be a very appropriate neural network, for example, predicting like the price of a house, for example, when you know like square footage of the house, or the let's say like the selling price of a house before the previous selling price of a house, or like let's say this is like the number of floors in the house or something like that, right? Because this is data that has like very little dimensions. There's only 3 dimensions to this data. But so you're familiar with logistic regression, right? Are you familiar with like logistic regression? So in logistic regression, basically the way that you make a prediction, right, is that you take all these inputs, like all these features, like these different dimensions of your input, which I'm going to call features here. Like let's say that this is like, would I agree on like the square footage of the house, the previous selling price of the house, and like the number of floors in the house? And then like what you did before is like you tried to like multiply each of those by some coefficient, like B1, B2, B3, and then you added some constant to that, and then like to that sum, you applied the sigmoid function to try to get, let's say that you were trying to predict whether this was a house that was like in the Bay Area or not in the Bay Area, right? So like you could probably tell whether a house was in the Bay Area or not based in the Bay Area, based on like the out of proportion of like the sales price to like the number of square footage, right? Like houses that generally have like a really high number for the selling price, like relative to the square footage, are probably going to be houses in the Bay Area, whereas the ones that didn't are probably going to be the ones in your data set that are not from the Bay Area, for example. And then you're counting on your logistic regression to like figure that out. Like there's this relationship between these two features. And then you put it through a sigmoid in order for you to like generate some number that's between 0 and 1, so that you can say that the ones that are closer to 1 are like, let's say that like you put it through the sigmoid and this is a really high number, and like the value you get is like 0.9, then you're like, this is highly likely to be a Bay Area house. And like if the number that you got was like a 0.1, then you say, well, this is unlikely to be a house from the Bay Area. And then like basically in logistic regression, you know, you would sort of train that so that you would get the right coefficients that you have to multiply x1 through x3 by. So does that make sense to you, Eric? And then, yeah. What's your name again?
Magdi?
Magdi?
Yeah.
Yeah, Magdi. And then Deborah, does that make sense?
Yeah, I have myself muted.
Oh, sure. Okay, good. So basically what a feed-forward neural network is that this activation here is basically the, like, you can sort of consider this to be like the logistic regression output of like 3 different logistic regression outputs from this data. And then the thing that makes it a neural network and not like just like many logistic regressions done over again is that you'll apply something called a non-linearity, which I'll go over here to each of these. And then the next layer over, you're applying a logistic regression kind of again to all these activations, kind of like in series. Does that kind of make sense, what I'm trying to say here? Kind of. Because like, if you sort of think about it, in sort of like a non, let's say that this was an image, right? The point of this is sort of to, in a hierarchical manner, extract features automatically. Like, let's say that one layer was like the image. Ultimately, what you need to do, like the way that you figure out like something is a face, is like you probably figure out where all the edges are, so you can figure out like where like, there's a nose somewhere in here, and there's eyeballs somewhere in here, ears somewhere in here, and if there's eyeballs, ears, and a nose of the human type, then it's probably a human face. Which means that like you have to sort of build things up from like the most basic elements, like where all the edges are, like where things are, like where the colors are, the textures are. And you figure out what is ear and like a nose and an eyeball based on those things. And then like then you figure out it's a face based on the fact that like there's ears, eyes, and a nose. And so like these are sort of that's an incorrect way to actually interpret these neural networks, but that is an intuitive way that I think is fine for like the first pass through these, which is that you're sort of building like levels of hierarchy and complexity in order to make a decision on like whether this is a human face or whether this is a house in the Bay Area or whatever. Okay. And so my whole point here is just that the usually convolutional neural networks, and they don't have to be this way, but like the standard like vanilla kind of convolutional neural network does a whole bunch of convolutional operations, and then does non-linearities to them at each different step. So a convolutional operation will be done to this to make this, and then this will be a non-linearity will be performed in this, and then it'll keep going until you get to, at some point you'll decide to just do affine transformations to your compressed image instead of continue to do convolutions. And then basically what happens is you get a score matrix at the end. So for example, if you're just trying to figure out whether a house is in San Francisco or a bit of the Bay Area or not, you'll just have one activation, and this activation will be some number. And once you put, like this number can be anything. It'll be like some number like between -1,000 and like 1,000. But once you put it through a softmax, it'll become a number that's between 0 and 1. And you can use that number to say, I think this is highly likely to be a house in the Bay Area or not a house in the Bay Area, right? So likewise, you can do, if you had several of these, you could be like, this is the node for something being a cat. And then this is the node for something being a dog. This is the one for being an airplane. This is the one for being a ship. And like, let's say that you're only concerned about 4 different classes: cat, dog, ship, or airplane, right? So then you would have numbers that I'm going to call your score. And then you'll pass in information here. It'll get processed through this neural network, and it'll generate these 4 numbers for you. And then you'll just say that the highest of these numbers is the one that you're going to call, that you're going to use to classify. So like if the number for airplane is the highest, then you'll say that this is going to be an airplane. Does that make sense? Okay. So
May I, that process makes sense on a high level, but how does it actually work? I mean, how does the application of all these different operations ultimately lead to a coherent result that gives you a categorization that's right? I mean, what is it about the nature of that cube that's kind of gliding across the other cube that gives you that information?
Yeah, so I'm gonna, it'll become more clear as we go, like learn the loss function, for example. And so I'll revisit your question once we finish talking about the loss function. But for now, I'm just trying to instill like an intuitive understanding of how the information could be passed from layer to layer.
Got it, thank you.
So, but let's say, for example, that this is your image and like you're looking for edges inside this image, right? And let's say that what you would want is for this kernel, which is currently this like random assortment of integers, you would probably want it to be something where there's like -1s. Like if you're looking for vertical edges, you might, for example, want the vertical, like the center column of this kernel to be all like +5s or something. I don't know, like +1.2, and then the like side columns on the sides to be like some negative number. And then like when the kernel passes over a positive like bar, it'll like sense like a bar that's vertical, right?
Yeah, that makes sense.
Right? So you would want that. So basically the output of that filter would have a high number in all the areas of the image where it sensed a vertical bar, right?
Yeah.
And then what you would do on the next convolution is like, well, all the places where there's a vertical bar in one channel and then like a horizontal bar in like some other channel, that is areas where there's an L, right? So that a kernel passing over something where there's like, let's say that you're looking for a vertical bar that is adjacent to a horizontal bar, then you could essentially, if with the right kernel in the layer that happens afterwards, have a place where all the elements of the filter, of the filter map light up in areas where there's an L-shaped, something that's an L-shape. But in order to sense L shapes, you first built that on top of sensing vertical and horizontal bars, right?
Yeah.
Right?
Yeah.
So you first have to learn something that's more basic in order to learn something that's more complex. So L shapes are composed of vertical and horizontal bars, and so forth and so forth. Okay? So non-linearities are really important because if you didn't, at each of these layers of your neural network, if you did not apply a non-linearity, such as these are not the only non-linearities available to you, but the one that we will use is something called a rectified linear unit. Basically, it's just this red one here, where anything that is less than 0 is like 0, and unless everything above 0 is itself. And there are many other types of non-linearities you can do. But the reason why you apply them is because if you didn't have non-linearities at each one of these layers, you're literally just applying a linear transformation upon linear transformation upon linear transformation, which overall is just one linear transformation. And so that would be computationally redundant and not useful to you because you can't build these hierarchies of representation. Does that point make sense, what I'm trying to say? Like some matrix multiplied by some matrix, and that whole thing multiplied by some matrix really can be summarized as just one matrix multiplied by that input. Like there's nothing special about doing this operation. But there is something special though about doing a matrix multiplication, putting that through some function. This function here is supposed to represent, maybe a little bigger. It's bigger. Like this function, when you pass the result of a matrix multiplication into a nonlinear function, and then use that as the input to a matrix multiplication, and then put that through a nonlinear, that becomes special. Now you are dealing with a neural network. That's why every time you do convolution, you do a nonlinearity to this, and then you do a convolution again to that after the nonlinearity has been applied. Okay. You'll see when I show you the example, this thing called max pooling. This is just what all it is. It's just a downsampling operation. It's very simple. So you can see this is a max pool operation where the max of each one of these quadrants gets put into its output. So here it's 8, here it's 3, here it's 4, and that's why the 4 is here. Okay? So just please stop me if that's not clear. So now finally we get to touch some PyTorch. Okay, so PyTorch, the module that you'll use to build your neural networks is this thing called NN, neural networks. I'm just showing you how to use one convolutional operation to a dummy image. So this dummy image is just 0, 1, 0, 0, 0, 0, okay? And I'm gonna pass this dummy image through a convolutional operation. And the convolution, the filter in the convolution is initially like randomly initialized. So it's just a bunch of random numbers, okay? Okay, and so I printed, so I'll run this. So I'll work you through this. So I printed out the input image right here. So it's a variable, right, of the slope tensor type. And then I create this class, and this class is what is, you'll put your neural networks into these classes, okay, like this, in this format, where there's an initialization, there's a constructor, and then there's the forward path through the neural network. This neural network is not really a neural network because all it has is one operation, just one convolutional operation, right? So I've initialized it, and I've stated the operation, which will be a convolution where number of channels going in is 1, and right, so there's only one channel here. It's just this is a two-dimensional matrix, so there's no, red, green, or blue channel. It's just one channel. I want to the output will just be 1 as well. So it'll create for me just one filter or one kernel, right? Because if I said that this was 64, it'll generate 64 kernels and apply it to this image. But I just want 1, and the kernel size will be 2 with a stride of 1. So can you guess what the output dimensions will be? If the kernel is 2, the stride is 1. What should be my output shape?
That's 2.
2, exactly. So imagine a 2 by 2 square that looks at this, and then it jumps by 1 pixel and looks at this, and then it's finished, right? Because stride is 1, kernel size is 2 by 2. So here's the output. And if you do the math yourself, if you take this is essentially the random kernel that it's initialized for me, and then this is the bias that is applied. So if you take this and you do like 0.295 times 1, and you add that to 0.3, you should get 0.6442. And if you take this kernel here and you multiply it by this, which should output for you a 0.45, and you add 0.45 to 0.34, you should get 0.7988. Does that make sense? Are you following the operation of the convolution?
What was the last part?
So just like we talked about there being bias terms, like this is the bias, right? The bias here. This convolution also comes with a bias as well for me, and so it's chosen like this one number for me as my random bias. So like when it applies this kernel, or sorry, this filter to this image, with the first operation, it's here, right?
Yeah.
Like this, imagine this set of numbers overlapping with these 4 numbers right here. This number here gets multiplied with this number here,
and then
it gets added to the bias, and then that's how it got this number right here. Right? Okay. So now we're gonna do the entire neural network. So if you look at this cell here, I've taken an input. I'm telling it that it'll take an input. It'll apply a convolutional operation to it with, and I'm anticipating that this will be a color image because that's why I've given input channel equals 3. I'm going to say that I want to apply 8 of such filters to it. Each of those filters will be size 5 with stride 1. And I encourage you to play around with this yourself.
What's the super part?
The super, this is a Python thing. I don't think this is not unique to PyTorch. It's like
a programming language thing.
Huh?
Like a programming language thing where you extend your classes into a subclass and you're calling the constructor of the previous class, of the parent class.
That's like inheritance?
Yeah, it has to be
I don't
inheritance.
think you should worry about that.
Yeah, yeah, I wouldn't worry about this right here. Just use it like, I guess it's you're putting the class that you want right here. Yeah, it has to do with class inheritance. Like for example, you might be having, you might make a child like class of this class, for example. And then that's, yeah, if you're, I should probably, yeah, I'll try to come up with a better explanation in the future for this. Super, just, I guess that's kind of thinking for now, but it's not related to PyTorch. It's related to just Python. Okay, so this neural network looks like this. I do a convolution, I do a advanced pooling, I do another convolution, then I flatten it out, and then I do affine, like affine transformation, affine transformation, affine transformation. So, so what this will look like is, this one will look like, it's like, you'll do this thing where you go from here to here twice, and then you'll take the end, you'll flatten it out, and it'll do like, you'll do this 3 times to it. So you can imagine this, at the end of it, this gets flattened out so that it's like a vector like this, and then you apply these affine transformations until you get to your output, which, because we have 10 different things we're predicting, that's why there's a 10 right here. What this operation here does, I put it, FC is the abbreviation for fully connected, which is I mean the same thing as affine when I say that. So this, essentially, this will initialize for me a random 10 by 32 matrix, right? And this will randomly initialize 32 by 64 matrix, and this will randomly initialize whatever this number is, times 64 matrix. And the reason why I'm doing that is because, or 64 times this whatever number matrix. The reason why is I'm anticipating that. So if you look at this, this 16, the output here will have 16 channels, and I've done the math here for you. Like after you apply to this convolution and pooling operation, the end, like, so imagine this box right here being 5 by 5 by 16. So this is 16, and this is 5, and this is 5, right? So the number of activations here is 5 times 5 times 16, right? And so if you flatten this out, you'll have a line of 5 times 5 by 16 activations in a straight line, right? And so if you want to do a matrix operation, a matrix multiplication operation to that, one of the dimensions of that operation will have to be 16 by 5 by 5, right? Which is why I've initialized the matrix at 16 by 5. 16 by 5 by 5 times 64. Are you following how this thing is like transforming the information? Okay, so in the forward pass, you call all these operations that you've initialized, and then you use them on your input X. So input X, first a convolution is done to it, then a nonlinearity is done to it, and then a pooling operation is done to it. And then another convolution is done to it, active nonlinearity is done to it, and a pooling operation is done to it. And then this view function here is basically my way of flattening it out. So I flatten the operation. I've shown you the math here. I've applied that one formula where you can predict what the output will be based on what the input is right here next to you. So the input image is of height and width 32. If you apply a filter to it with no padding, then you just do 32 minus 5. The stride was 1, so you divide by 1 plus 1. So the output was 28. So it got compressed in something that was 28. So after the first convolution, your image representation was 28 times 28 times 8, okay? After your next one, and the pooling operation downsampled that to 14, then your next operation took that 14 by 14 by 8 representation of the image, and then compressed it into something that was then 10 by 10 by 16. And then the max pooling operation took it and made it something that was 5 by 5 by 16. Are we still following? Okay. And then we did the 3 or the the 2 1 F2 F3, yeah. Then we applied the 3 different linear transformations to it, the affine transformations or fully connected layers. These are all synonyms. The last one, you notice I did not do a ReLU. I only did it for the first 2 linear transformations because this one I'm going to allow it to be positive or negative numbers.
Sorry, could you explain that out channel? That's the same as the filters that you were talking about before.
Where are you looking here?
Like out channels equals 8, out channels equals 16. And your convolutional. So,
go down?
No, further up.
Further up. Oh, yeah.
It's like in the parameters. Yeah.
Oh, out channels. Okay, so remember how we talked about how this is the number of filters I'm choosing.
Okay, yeah, that's just okay.
Yeah.
All right.
Yeah. So in my example here, I chose it to be 1 because I wanted the output to just have 1 channel.
Mm-hmm.
Had I chosen this to be like 8, there'd be 8 of these. Yeah.
And they're all random. The kernel.
They're initialized randomly. Right. You did the hardest part. Okay.
I have a question.
Yeah, go ahead.
How do you choose the number of channels? What's your reason for choosing like 8 versus 1 or whatever?
Yeah, so that's kind of like so those kind of things are it's kind of arbitrary, and so this is kind of what there'll be a bunch of things in deep learning that are kind of arbitrary choices, and there are set architectures that like somebody with much more ability to experiment has done already for us, like Google, for example, who have chosen these architectures that are very efficient, where like they have chosen like the best like number of like kernel size and like number of convolutions to do, or like number of filters, stuff like that.
Okay.
But here I'm choosing like a random one just to show like what they do.
Okay.
So this I could easily change this number here to like 16, and then I'd have to change this number here to 16. And then I have to change this number here to like 32, and like this number here to 32. And essentially by doing that, I would have made like a neural network with more parameters, right?
Mm-hmm.
By doing that. And perhaps by doing that, this neural network would perform better maybe. So this is just like an arbitrary one. Like this is just a made up neural network for teaching purposes.
Okay, got it. Thank you.
Okay, so I will go ahead and create that class. Okay, so after this, I'll take a bunch of questions about like how neural networks actually work. But first, I'll teach you what a loss function is. So all of these parameters here are randomly initialized. So how is that supposed to give me right answers? And that's what the loss function is supposed to answer. So let me first define what, like this is my own definition of a loss function I came up with. So the loss function is a scalar calculated from the output of your neural network and the ground truth labels that requires the neural network to do what you want it to do in order to be minimized. This means that if you change your parameters in the opposite direction of the gradient with respect to the loss, the neural network gets better at classification. Does that definition kind of make sense? For example, let's say I'll go through the rest of this in a second. So let's say that my loss function was negative. So let's say I was only doing 2 classes, right? And I'm just saying like dog or cat. So there's only 2 classes. And my loss function is 1 minus, so 1 minus, and this is the sum across like the batch. That's why it goes from 1, this is the sum across all the classes. And let's say that I had like for cat, y was 1. So basically, like if I showed you an image that was a cat, basically the loss from that image was the probability that you assigned to that being a cat. So if your neural network was randomly initialized, by expectation, the probability that you would assign to some image being a cat would be what? 50%. Yeah, 50%, right? So 0.5. Because there's only 2 choices, right? Dog or cat. And if it was dog, cat, and like boat, then by expectation, the probability that you would assign to the image would be 0.33. So let's say that I'm going to simulate here, for example, for you. My neural network assigns a score of 10 for the dog and a score of 10 for the cat. When that's normalized, you get 0.5 and 0.5. This cross entropy, loss function, what it'll do for you is it'll go ahead and like normalize your score for you. So when I run this, you'll see you get the same result whether your score was 0.5, 0.5, or whether it was 10 and 10. And this is supposed to simulate what comes out of your neural network. So it's supposed to simulate this thing right here, this last X here that comes out of the neural network, the one that you return. And so if I say something is 10, like I give a score of 10 for dog, score of 10 for cat, and this is in reality let's say a cat is the one that comes first. And I put this through my loss function or my criterion, which was a cross entropy loss. Negative log of 0.5 is 0.69, which is why the output is 0.69 here when you run this cell here. Okay. And so your neural network is going to want to make this number here as high as possible, because the higher this number is right here, the one for cat, the lower this loss will be. Are you still following? Does everyone still follow what I'm trying to say here?
Yes.
What this cross entropy loss does for it is it does something called a softmax operation. What a softmax operation does is, let's say you give it an vector that's 10, 10, it'll normalize it so that all the elements add together to be 1. So if this was 10, 10, 10, like with 3, it'll turn it into like 0.333, 0.333, 0.333. Or if it's just 10 and 10, it'll turn it into 0.5, 0.5. And likewise for anything else you do. Like you could even be like, this could be 10 and 20, and it'll turn that into something that also adds up to 1. But the number, the second, the one that's bigger will be a bigger number, obviously. So it'll turn this into a probability distribution over the classes. Make sense? Okay. So what the loss function will do is, this is just something called numerical stability, which means like if so the softmax, this is the softmax function here. Like this is how you turn like some arbitrary vector of numbers that are, some of them can be negative, some of them can be really big, some of them can be really small numbers, but this is how you take any vector of numbers and turn it into probability distributions such that all the elements, when you add them all together, equals 1. And so like basically when you do this to some score, like, you know, let's say that there's dog, ship, cat, and I've given a score of like -10, +10, +100. I'll have to turn that -10, +10, and 100 into something that adds together to be 1, because I'm going to interpret that as the machine learning algorithm saying that I think that like the ship has a very low probability, the cat has like also slightly higher but also low probability, and then the last one, like the 100, being the one that I think is the most probable, like being a high probability. Okay. And so this is the loss function. So basically, we have by establishing this loss function, we've essentially created a scalar that if the scalar is smaller, it will mean that this neural network is doing a better job at classification. Are you still following along? Yeah? Okay. All right. So what I'm going to do here is I'm going to establish a training loop. So what the training loop does is every single loop through this training loop, it's going to grab some 4 images and 4 labels, the correct labels. It's going to pass the inputs, okay, through the neural network right here. The inputs go into net. Net is our neural network. You get the outputs out. You put the outputs here and the labels here into our cross entropy loss function. You get the loss. And just like in the very first cell I showed you, you can do loss set backwards. And basically, this will calculate the gradient on every single parameter inside your neural network. Like whether you have like a couple hundred of them, like I have here, or a couple million of them, like in a real life example. And then this optimizer.step here will essentially apply that gradient to every one of the parameters with this learning rate right here. So you can, optimizer was defined up here when I demonstrated to you. Don't worry about this momentum for now, that's more advanced. But the stochastic gradient descent algorithm is what's being used here, that W equals W minus learning rate times gradient, which I showed you before, is being applied to every single parameter inside of net. That's why you told the optimizer which ones you're interested in updating. That's why this net.parameters exists here. So at each iteration, it calculates the loss and applies the gradient with respect to the loss to all the parameters. And as you do this, your neural network, the loss will decrease because it's doing a better job at labeling the images. And so any questions about that? So as you look through this, I'm going to pretty much just look at the loss that happens every one of the epochs. So I'm going to go ahead and just run this training loop, and you'll see this thing start to train. So it's going to take a little time because I've decided to do 5 epochs here. So the loss starts off at 2.25. Why does the loss start off at 2.2? Any clues? I sort of explained it already with the binary classification example. Like, why is it the first loss you get 2 point, and then it gets lower from there? Well, the reason is because negative natural log of 0.1 is 2.3. So basically, what it's saying, what that means is that initially it doesn't have any idea what it's doing because all the parameters are random, right? So like by expectation, the sort of probability that it will give to like dog, ship, cat, boat, whatever will be 0.1 by expectation. And so it'll be, so the loss for that will be approximately 2.3. And so that's why this is 2.2, because it's a little bit better than that. And as it gets better and better, the loss gets lower and lower and lower. As it gets better at classifying them correctly, because that's the only way to get a loss that's lower is by assigning a higher probability to the correct class.
You can see the step size and the loss are getting smaller as well as it kind of.
So I'm printing out here the epoch here for you. And
yeah. No, I'm saying so the loss is improving by smaller amounts as you circle.
Oh yeah. You mean it's kind of going like this?
Yeah, it's doing like gradient descent.
Yeah. Okay, so that's how you get the right answer, is that you start off random and then you slowly update your weights towards the right answer. That's how these things work. Oh, actually here, I screwed up here. I wasn't supposed to train this just yet. Let me reinitialize my neural network. I'm going to erase all the valuable work I've just done. So I just reinitialized all my weights just now because I wanted to show you something. So right now, these are all going to be wrong, right? Because actually, this is all right for some reason. Why did I get it right? Oh no, so this is the ground truth. Sorry, I'm giving you. This is the right. These are the right answers. This is just me showing you what the outputs look like. These are all numbers here that are they're like they don't add up to 1. Like they look like this, and they're of size 4 times 2 because it's the batch. And like basically these are the scores that's given to each one of the classes. Because remember, there's 10 classes that go from like, I forget, it's like one of them was like cat, and one of them was like ship and whatever. So there's 10 of them. So the number of columns here is 10, and the number of rows is 4 because your batch size is 4, right? These all get squashed in that softmax function to become some positive number that all adds up to 1 across each row, right? So that's what that's just letting you see like what things look like. Okay, so I think this is what its prediction was. So it's predicting dog, and that's obviously wrong because this is a randomly initialized neural network. It's of course getting all wrong. And then let's see, what is the? So what would you expect? What is like? What is how well? What kind of accuracy do you think it'll get here? 10%, right? Because it's randomly guessing, right? And this is just your way of saying like how accurate it is for each of the classes. It takes a long time. Right, it gets 100% dogs right. That's probably because it's trying to say that every single image is a dog. So it got dog 100% correct, and it got everything else 0%. Right. Okay. And then this is a way to visualize that first set of filters. So if like let's say that you turned like those random numbers inside of each of your randomly initialized kernels and just looked at it as colors here, like this just looks like a random assortment of colors, right? Yeah. And as it should, because these are all random filters, right? So what I'm going to do here is now I'm going to train it. There we go. Okay, so I'm going to train this. And so we're just about finished here. So I'll take questions. So I promised that after the loss function, I'd answer more questions. Any questions about as we're waiting for this to train?
I need to even digest it a bit more, and then I'll come back with questions. Okay.
Well, like kind of what was the first thing you were going to think about when you went home and tried to digest it?
I think transitioning. I got everything very well before we, I guess, transitioned from discussing about the kind of the idea of having the kernel and shifting it to the image and training the weights, moving to this layered neural net with the activation functions. I think I need to maybe understand a bit more how these activation functions work. I understand that they kind of give you a score to maybe use some thresholding against it in a very basic sense. But then when you layer them together, when you stagger them, I guess I understand that step a bit more of.
Yeah. Fair enough. Yeah.
Do you understand why you would use a convolutional neural network versus like a fully connected one? Or why one is more appropriate than the other for computer vision?
Not at the moment.
I don't have the great intuitive explanation for that. I think that for convolutional neural networks, you're kind of like looking at subregions of your image at a time because of the kernel.
Yeah.
So it gives you a bit more robustness when you're doing like computer vision. Because if like you're trying to look for a tumor and it's like on the upper left-hand side of the image versus the tumor on the bottom right-hand side, it'll be okay because of the convolution.
Yeah. Okay, that makes sense.
Yeah, I mean, essentially, technically, if you try to do this, like using all affines, like if this was just all affines, technically it could probably, with enough data, maybe learn the same sort of like mapping, but then it would be so much harder for it to do because you would have to learn that this pixel is next to this pixel, whereas here you've already encoded that into your architecture. If that makes any sense. Like, it doesn't automatically know that like one feature is like this is like some pixel that's next to some other pixel necessarily.
Okay, are you done?
Should be done. I think I have one more. Oh. Sorry. I think it's, yeah, they should be done now.
The loss is going up.
Loss is going up?
Oh no.
Well, you can expect some, yeah, so it went up from here to here. But that's normal. I mean, because it's like looking at different batches every. I mean, that's why it's called stochastic.
So when the loss goes up, does it do something to like go in the opposite direction or something like that? Or
It means that you updated the weights in such a way that it got
Pretty random.
It's pretty random, yeah. It's just kind of have to just hope for the best.
I think it's because the other kind of gradient descent is a lot more computationally expensive if you're doing it deterministically.
Yeah.
You have to, you're comparing it to every other.
Yeah, you're
point,
gonna have the memory.
and so you use a
Exactly.
stochastic process, and so you get sometimes that it might overshoot on the minimum and then try and come back. But then,
We're almost done. There we go. We're done. Yay! So our final loss was 1.05a. So it's not great, but let's see what it says the predictions are here. So was that for this, or I think cat, ship, car. So I got these two wrong. I got these two right, I guess. Let's see what percentage of the images got correct. Hopefully more than 10%. 62%. Yeah. So that's somewhat better. And then let's see what like the distribution or the different classes are. Yeah. Okay. So it did the best at car, or no, it did the best. Yeah, with cars. And then let's see what the kernels look like now. So they're somewhat more structured. Like they still look a little bit, but you can see like they're definitely not as random looking as the initialized one. Like for this one, for example, like there's a bunch of reds all together. So like if this was something that told you that there was some red down here and some blue above here, this would make sense. Like this is something that would activate with like more blues on top, more reds on top. Like this would make sense to be some sort of like dark diagonal line detector. And this would sort of make sense to be, I'm not just making this up, right? So like this looks like definitely more structured and less random than the kernels you had before. And so that's what it's learned so far. And if this learned to have a smaller loss, like we only got to an accuracy of 62 and a loss of like 1. And so my intuition would say that like if you continue training such that it would be a better classifier, or you had like just a better neural network, then these would look even more structured compared to like.
So what are these again?
This is me looking at the first layer kernels. Because remember those first kernels, I think there were, how big were they? They were size 3 by 5 by 5.
Mm-hmm.
Yeah. So that's why these are all size 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And they're colored because they also they have 3 channels to them. So that's why I was able to display them as a color.
Right.
And so and then there were 1, 2, 3, 4, 5, 6, 7, 8 of them, right? Because there are 8. I chose to do 8 kernels to begin with.
Mm-hmm.
And so that's why there's 8 of these. So I'm having you like kind of visualize the kernels that we learned for the first layer. I could do the same thing for the second layer, but I think the first ones are the more interpretable ones, because they should be like edge detectors and like texture detectors and stuff like that. Yeah. Okay. And that's it. That's the end of the introduction. So there's more if you're interested, because obviously I'm going to teach batch norm and deconvolution or convolutional transpose as well. And so, but I think that's all we have time for now. Okay. Cool. Great.
Thank you. That was very interesting.
Oh, no problem. Thank you.
Are there any other resources for like maybe brief overview before you guys go more into it?
Nice YouTube videos.
Yeah, like the resources for learning this stuff all over the internet. So if this wasn't a good way to learn it, then someone out there will have some other flavor or ingredients for teaching that might resonate better with you.
also check out so 281 have all their lectures online, all their like notes online, and so they're pretty comprehensive.
Yeah, I helped start with a vanilla fully connected neural network.
Thank you, Carson. Thank you, Greg.
All right, no problem. All right, good luck.
All right, thanks,
Talk
guys.
to you later.
Bye.
See you guys later.